Everyone's doing really well. I'm doing alright. I had a nice day. And now I'm prepared enough, I think, to create a quick video discussing how timers work on the ESP32 microcontroller. So we're just going to do a very introductory session, but we're going to be looking beyond the delay function that you may be using in Arduino code. So if you've been writing code in Arduino for ESP32s and you want to try and understand a little bit more about the hardware and what's going on behind the scenes, not on a register level but on the hardware abstraction level or layer, then hopefully this video will share some insights and also some tips as to and tools as to where you can read and find more about how these timers work. So I have this code that I've written here, and we're going to walk through it step by step, adding comments and what the purpose of each part of the code is for creating a very simple application that just counts up every 2 seconds, and how we can change this and configure this differently as well. So first of all, we have our it includes what sort of libraries or external tools we want to include for this program. We have our standard I/O. I don't actually know if that's needed or not, so that can be something to find out later on. Is this needed or not? But when we set up our template, when we set up our programming environment using VS Code, as I showed in my last video, I think this gets added into our template by default, so we're going to keep it in. But it could be something to look into. Is it actually needed? Next, we want to include our FreeRTOS main header, I suppose, and our tasks, and this is needed so that we can run FreeRTOS on our microcontroller. And you don't have to do this. You can use, I think it was a super loop, is what it's called. Well, that's going back a while, where you just have a main loop and you don't actually have an operating system running on your microcontroller. But when it comes to developing larger, more complex applications, using a real-time operating system and tasks, I think, is a really good way of managing different behaviors and how tasks are executed. It also makes your code more sort of more modular. You can break down different tasks or things you want to do into chunks, and so it's easier to program and develop and debug as well, which is really good. So we want to include our real-time operating system framework, I suppose, our software tools that we're going to use. We want to be using the general purpose timer that is a peripheral that the ESP32 C6, and I think all ESP32 families, but specifically in this case for the C6, have. That's what I'm going to be talking about. I even have some notes here that we can go over. So we want to include that header file and our ESP log header file as well, so we can actually see the results in our serial monitor when we're running a program. So with those 5 different header files included, we can actually get started. We've created a constant character tag. It's a character pointer or a character array, which is why we can have multiple characters. In this case, you can call it simple timer counter. You can call it timer underscore counter, as I had it beforehand. We want to create a static volatile counter variable. It's an integer type, and we're going to set it to 0. The reason our variable is volatile is because our data, our count data, is going to be handled by a hardware interrupt that we're going to set up. So as our timer is running, there is an alarm that will periodically go off after we meet our timing requirements. After, in our case, however many ticks have gone past, or however many seconds, and that's going to trigger a hardware interrupt, which we have to create a function for that's going to modify these variables. So we've got a counter and we've got a flag as well. There might be a different way of updating variable with the flag, but this is a very easy way to do it. Maybe it's not the best, I'm not sure, I have to look into that. So what we want to do here is create a callback function. So when our timer, it's counting up, when it reaches a certain value, it's going to trigger our hardware interrupt, which calls our callback function that we can create. So it is of type, it's a Boolean type static function. It returns a Boolean, and also we have this IRAM_ATTR, which just means we want to create this function, we want to load this function into our instruction RAM. We don't do any sort of data modification, so we can do that. And you see that here when we're only increasing our counter and we're setting our new count flag to true, and we return true. And actually, I don't know why we return true. I did a little bit of reading into it, but not any more than a Google search. And I don't remember why it's needed, but there is a reason. But I don't think it actually does anything in this function. I don't think we're utilizing this part of the function very well. I'm not sure. When we set up this callback function, we have to pass in these parameters. We have to have our timer handle, a constant alarm, event data type, which we pass a pointer, a reference to, and we have this this user_CTX parameter. Is it an argument? I think it might be an argument, but I can't remember what that does. But we don't have to worry. It's just this sort of setup you have to do if you want to use hardware interrupts with your alarm. So when our timer alarm triggers, it's going to increase our counter variable, which we have here. It's going to say we have a new counter, we have a new count, and that's going to be in our, when we print that out to the user, that's going to be a flag that we check to see if there's a new count ready. So we come into our main application, and oops. Sometimes I will write, oh dear, here we go. I prefer this sort of formatting a little bit more. What we can do here is we can just say something. The application has entered its main function, the app main. This is the starting point for the application that we run on our microcontroller. So maybe we can just say hello world, our application has started. The next thing we want to do is we want to create our timer handle. Coming back to our notes, we will read through these, I think, a little bit. I probably should have done this first. This is just through reading through the technical reference sheet or manual that is provided. If you just look up ESP32 C6 technical reference menu, this is some of the highlights that I've written about the timers in a very introductory manner. First of all, there are 3 clock sources on the ESP32. One is a phase-locked loop circuit. We have our crystal oscillators, and we have also resistor capacitor oscillators as well. And we can use a multiplexer to select what different clock source we want depending on our system requirements. Maybe we need different performance requirements for certain applications that we're developing for. And this is where you have to understand the context of your application rather than because that has a strong influence, I think, on the code that you write. They're very interrelated. It also allows us to manipulate our clock sources to achieve different time divisions. We can increase or decrease our clock count. I'm pretty sure we can increase it. We can definitely divide our clock count with dividers. And I seem to remember, I didn't read again too much into it, but we can use a phase lock loop to increase our clock source, but we're not going to go into that in this video. This is then used as our time or count. This is then used to time or count different operations from functional modules such as the CPU, Wi-Fi, or Bluetooth modules. In our case, it's going to be our general purpose timer module, which is really which is what we're programming in this video. So there are high and low speed clock sources as well, and they can be utilized for different, if you've got high power applications, low power applications, but we're not too worried about that here. Then there are two timer groups. There's timer group 0 and timer group 1 for the ESP32 C6, and it's probably the same with just the standard ESP32, but you will have to verify that with the datasheet because there might be some differences. I think our standard clock speed is 40 megahertz and it's sourced from our external crystal oscillator. There is an 80 megahertz clock derived from our phase locked loop. If we were to select it, and there's a 17.5 megahertz clock available derived from our RC clock. So there are different time sources that we can use, and we're just going to stick with our 40 megahertz clock. And then there are different ways we can interact with them, which we're going to go back to the code now and have a look at. So there's just a simple clock that counts up. We can have a timer that triggers a one-shot alarm, and we can have a periodic timer alarm by APB. I don't really understand what that meant in the technical reference manual by the, I think it's advanced peripheral bus, which is okay, but that's what we're going to be doing essentially, is using hardware interrupts and periodic alarms to create our counter. So one thing you may notice as well is there's a lot to embedded software design, and there's so much you can research, and so trying to understand all of it is, you could spend a lifetime really getting into the details about how things work, and I do encourage you and myself as well to actually do this. But it's okay not to know certain components. And it's okay to look back and improve upon. And so maybe I haven't thought about what I'll do next in my next tutorial video, but it could be a more advanced look into, or like a deeper dive into how timers work, or it could be something completely different. So where we got up to is just talking about this timer handle. So this is our general purpose timer that we talked about. We want to create a configuration variable, I suppose. If we just put our mouse over here, we can see that it is a struct. GP timer config is a struct, and what we're doing is we're configuring different variables inside the struct so that we can pass that into our new timer function, which is just below, and then the microcontroller, sorry, the ESP-IDF framework will actually handle the rest. So we don't have to worry about reading and modifying registers to set up our timer. We're only working on the hardware abstraction layer. So we want to set our clock source to our GP timer clock source default, which I think was our 40 megahertz clock, but you can change this depending on your requirements as needed. We want to be counting up, so we set our general purpose timer direction to count up, and we can set a resolution as well of 1 microsecond ticks or 1 megahertz resolution for our clock. We then pass our timer handle and our config. We pass by reference into our GP timer new timer function, and that's going to create a new general purpose timer and return the handle. It says it in the documentation anyway when I hover over. So with our new timer, we actually can move on to creating our GP timer event callback structure, and we set our on alarm to our timer callback function. On alarm equals timer callback, which is the function name that we created up here. So when our timer counts to the alarm count that we specify, what function do we want to call? What interrupt will be called, and what data is going to be manipulated is what we're saying here. So our next part of our code here, we have our GP timer register event callback. So this is where we pass in, we tell the microcontroller what timer handle that we're going to be using, because you could be using the 0 or the 1 handle. We pass a reference to our callback, and there's also a null that I've written here, which is our user data. We're not passing anything into our user data, which is why I wasn't worried about this this argument here in our callback function. Once we've done that, we can set up an alarm configuration. So how do we want the timer to how do we want the alarm to work? We've set up how we want the alarm to respond, but here what we can do is set our alarm count in ticks. Because we have a 1 megahertz resolution or a 1 microsecond ticks, we've got however many numbers that is, 200,000, 2 million, I think that might be 2 million. My eyes aren't doing too great today, so I'm not going to try and count the zeros, but it's 2 seconds essentially is how quickly our timer will, our trigger, and we can change this if we wanted 3 seconds to 3 million. We can change it to half a second if we wanted to 500,000 counts for our timer. We set our reload count to 0. We don't actually have any documentation about that, and I wrote this code about a week ago, so I don't remember why. But if you look up the ESP-IDF docs, it'll tell you why. I assume it's so that we can reload our counter. That's what it will be actually. Our reload count here. Alarm reload count value effect only when auto reload alarm is set to true. So what we can do is I think our alarm will start counting from 0 all the way up to 500,000. Our timer, sorry. And then when we reload our timer, I think we can start from a different value than 0. So maybe you want a longer time event for a one-shot action, and then you want to start counting up from a different value, which is where we can set that here with our reload count. And then we also want to reload on alarm. We set that to true, so our timer is constantly running. It's constantly counting up to 500,000 in this case. It could be 2 seconds, which is what I had before. So that's how we configure that. Then we set our alarm action. We have to let a function know what general purpose timer handle we're using again, and we pass in that configuration as a reference. We can then go ahead and enable our timer. We can start our timer, and then we enter into our while loop for our task, our main app task. The first thing you'll notice here is that we check our new count flag to see if it's true, and if it is, that means we've got data that has changed and our counter has increased. We can go ahead and print that for the user using a printf statement or a ESP log statement, I'm sure will work. And then we want to set our new count flag to false because we don't have any new data. And then I've just added a slight delay, a 10 millisecond delay to this function. That could be because maybe you want to have other tasks running. If you've got a more complex program running on your real-time operating system, but it doesn't matter really too much for this video. So this is how you can program a timer. If we want to come down to our tools here, we can build our project and just verify that there are no errors. It's going to take a while. This is running through a complete build. Of the ESP-IDF framework that's provided. We do have an error, actually. And that is this here, which was probably just a typo. If we go ahead and build this project again, it's not going to take that long as well. Perfect. So if you go ahead and run this program, you will have a timer that calls a hardware interrupt, your callback function, interrupt service routine, or your callback function every 2 seconds or every amount of counts that you set. And because we have our resolution set to 1 microsecond ticks, we can really easily do the maths there as to how often we want our alarm to call and then our timer to reload. Then when we come down to our main task here, we just have a 10 millisecond delay, and we are polling a flag to see if our counter has changed, and that will print the new count value for the user. So I hope this video has been useful for you. If you have any feedback for me, please let me know. I hope that by the time I do 10 or 15 or 20 of these, that they'll be better, and that I'll get better at them. Maybe the production quality will be higher, but we'll see. And please stay tuned. Feel free to subscribe if you want more content around embedded systems and you want to join this sort of, this learning but sort of pathway with me, as I sort of document some of the findings that I find out about embedded systems, which is really cool, and some of the stuff that I've learned in the past and am having a refresher on, and some of the sort of ideas and knowledge that I'm applying into my work that I'm actually doing at the moment. So thank you for watching, and I hope to see you next time.